All right, hello. So this will probably be the first video you see where I've got my new microphone. While I was uploading the lectures for this week, I had come to the decision that I wanted to re-record a couple of these. And so there'll be a couple more videos after this where I'm using the computer mic, but then shortly after that, I will permanently have this microphone. So like I will probably say in the near future, hopefully this will help with a lot of sound issues. This will also mean I can talk while facing the board and not worry about being heard. So, section 2.1, section 2.2, video 1, we introduced this idea of invertible matrices, and we saw how to find the inverse of a 2x2 matrix, and then how we can use that to solve a matrix equation. So what I want to do in this video is lay the groundwork for how we can find the inverse of matrices of higher dimension. And so what we're going to do is we're just sort of going to prove, our goal is going to be to prove one main theorem, which will tell us exactly when a matrix is invertible and how to calculate its inverse. Then in the next video, we will calculate some inverses of larger matrices. So we need to introduce a new type of matrix, which we will need for the proof. So we say that an n by n matrix that is obtained from the identity matrix after a single row operation is called an elementary matrix. So this is a matrix where I take the n by n identity. So in this case, we're looking at elementary matrices of size 3. And I do one row operation. So here, notice I did -3 row 1 plus row 2 to get this matrix. Here I did just a scaling operation, and here I did a row swap. Each of these would be an elementary matrix. So why do we care about elementary matrices? Well, notice that first off the bat, each elementary matrix is sort of unique to its corresponding row operation, right? So like each one of these elementary matrices is associated with the single row operation that we used to get from the identity to this matrix. So keep that in mind. And so what I want to do is talk about two facts about these matrices that we will need. One of them I think is pretty cool. Well, they're both pretty cool, but one of them I think is really cool, especially given the context of what we've been doing. So it turns out that if A is an m by n matrix, then any row operation on A can also be performed by multiplying by the elementary matrix associated with that row operation. So what does this mean? Well, this means that if I were to do a single row operation on a matrix, the new matrix I would get could equivalently be found by multiplying A, and I'm going to say here, multiplying by the elementary matrix on the left. Multiplying by the correct elementary matrix on the left, and we should get the same matrix out. So I want to do an example with this matrix here. We'll call this matrix E1. And so I'll give you a matrix A, and then we can sort of verify that, in fact, this is doing what we think it's doing. Actually, maybe for the fun of it, because I think this is cool, we'll do a couple. So we'll also do a row swap just to see that this actually works with row swaps too. So we'll call this matrix E2. And so remember, this row operation should be row 1 swapped with row 3. And this row operation should be -3 row 1 plus row 2. So what I'm going to do is I'm going to multiply A on the left by both of these matrices, and we'll verify that the matrix we get out was the matrix we would have gotten by doing each of these row operations. So we'll let A be my favorite example matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we'll say E1 times A equals, well, we'll have to do the matrix multiplication dance here. So I'll write out the matrices times 0, 0, 1. Oh, nope, that's E2. I don't want to do E1 times E2. I want to do E1 times A. 4, 5, 6, 7, 8, 9. All right. So what matrix does this get us? Well, doing our matrix multiplication dance, notice this first row is just going to go across the first row of A and actually not change it. Right, so this 1, 0, 0 is just going to continue to match up with 1, 2, 3, 1, 2, 3, 1, 2, 3. All right, so now notice what happens with this second row of E1. Every time I do the dance, I get -3 times 1 plus 4. Then I get -3 times 2 plus 5. Then I get -3 times 3 plus 6. And so I get that for row 2. And now notice this last row, when I match it up, it just matches up with the bottom row of A. And so I get 7, 8, 9. And so notice here, this matrix was the matrix obtained from A by performing the row operation -3 R1 plus R2. So sure enough, works there. So let's look at it for one more, just for the fun of it. So notice what's going to happen here when we multiply this matrix by A. So this time, when I go across the first row, this first row of E2 is going to match up with the third row of A. Second row is going to stay fixed. And now the last row, well, that's going to match up with the first row of A. And sure enough, the elementary matrices work in the way we think they should. So fact one that's very important about this, if A is an m by n matrix, then any row operation on an A can also be performed by a sequence, or by a single multiplication by a single elementary matrix. And so what this implies in particular is that if we multiply by a sequence of these matrices, we can actually row reduce A, or find a row reduced version of A. So keep that in mind. We'll need to call on that later. So I want to state one more fact that we won't talk about quite as much. So fact 2. Each elementary matrix is invertible. And so it actually turns out that the inverse of each of these elementary matrices is just the opposite row operation, or the opposite row operation that we performed. So for example, the inverse of E1 would be the matrix corresponding to 3R1 plus R2, which would just be this matrix. So this would be E1 inverse. This would be E1. So E1 inverse, E1. And then if we multiply these out, notice in particular, this 3, 1 matches up with the 1, negative 3 to give me 0, 1, 0, 0, 0, 1, and we're good. So, important fact, every single elementary matrix is invertible, and it's always associated, its inverse is always associated with the opposite row operation. So that is the, I guess you can think of it in a sense as like the row operations that would sort of cancel each other out are inverses. So here, notice 3R1 plus R2 would cancel out negative 3R1 plus R2. And so that's why they're inverses of each other. All right, so using fact 1 and fact 2, we can now state our theorem, which will give us sort of an outline as to how to calculate the inverse of a matrix. And so we're actually just going to end, we're going to end this lecture by stating this theorem and proving it. This will be one of the more involved proofs we've done so far, but I think it's very important because the sort of walking through this proof actually will give us a very good indication of how we're going to actually find the inverse of A. So, without further ado, so an n by n matrix A is invertible if and only if it is row equivalent. And so remember, row equivalent means it can be row reduced to the identity matrix I sub n. So a matrix is invertible exactly when we can row reduce that matrix to the identity. And so on top of that, this tells us how to find the inverse, because the same sequence of row operations used to reduce A to the identity can be used to transform the identity matrix into A inverse. So, what this theorem tells us, we have a way of checking if any matrix is invertible, right? We just row reduce it and ask, did we row reduce it to the identity? And remember, this is very nice because the identity is always the matrix we're sort of shooting for when we do our normal row reduction algorithm. And so if we can reduce it to the identity, well, we just keep track of the row operations we used to do that, and then we perform those same row operations in that same order in order to transform the identity into A inverse. And so this second part of the theorem is what we'll use to actually find an algorithm for finding the inverse, which, like I said, I'll discuss next video. I'll just prove this now. And so notice that because we have this if and only if here, if and only if, we have to actually show two things in this theorem. So the first thing we have to show is that A being invertible implies that A is row equivalent to the identity, And so this one won't be terribly hard. The other thing we have to show is that A row equivalent to the identity implies that A is invertible. And so this one will be the more interesting one, and this will give us the give us the algorithm. Well, it'll give us the reason that we have this nice algorithm for calculating A inverse. So I'm first going to show 1, and then we'll come back and show 2. All right, so as we've already seen, if A is invertible, then the matrix equation AX equals B has a unique solution for all B in Rn. So what does this mean? Well, this means that then thought of as a linear transformation, A is 1-to-1 and onto. But these two facts together, we've already shown with an n by n matrix. So 1-to-1 and onto means, well, so 1-to-1 means that when we reduce A, we get a pivot in every column, or a leading one in every column. Onto means we've got a pivot in every row. Well, and so those two things together means that A is equivalent to, or A is row equivalent to the identity matrix. So if we can show that the linear transformation is 1-to-1 and onto, we know that this must be true. All right, so like I said, this was sort of the easier direction. If A is invertible, then A has to be row equivalent to the identity matrix. So now I want to get to the interesting part. So fact number 2. So now we're going to show that if A is row equivalent to the identity, this implies that A is invertible. All right, so remember that with these elementary matrices that we introduced, multiplication by a single elementary matrix gives me a matrix that was obtained using a single row operation, right? So if I start with my matrix A and I perform one row operation, I get a matrix E1 times A. Well, so let's say I performed another row operation on this matrix, I would get a matrix E2 times A, E2 times E1 times A, right? So this would be the matrix I've obtained after performing 2 row operations on A. Well, let's say I just performed all of the necessary row operations to get to IN. I'd get something that looks like this. So I'd have multiplied A consecutively by P elementary matrices corresponding to each of the row operations needed to row reduce A to the identity matrix. So next, remember that each one of these elementary matrices is invertible. So we're going to use this fact, and I will discuss it a little more in the next video. But if each of these matrices is invertible, are invertible, then the product E1, other order, EP times E2 times E1 is invertible. So if a collection of matrices is invertible, then the product of all of those matrices is also invertible. So that means that this product has an inverse, and so I can multiply on both sides by its inverse and get that A is equal to EP times E2 times E1 inverse, so the inverse of whatever this matrix is, times the identity. But the identity times anything is just itself, so I can actually just drop this identity. Well, and so now I know that A is equal to the inverse of this product. So why not just take the inverse of both sides? Because I know that this inverse exists. And so this implies that A inverse is just equal to the product of these elementary matrices, EP through E1. And so notice in particular that if I wanted to multiply the identity matrix on the right here, then this proves the last part of the theorem, that this product here is just equivalent to performing each one of these row operations on the identity matrix to get A inverse. And so this shows, or gives us sort of the remaining part of the proof that, well, we know that A inverse exists because A is equal to this invertible matrix. And we know what A inverse is. It's just the product of these elementary matrices, which, remember, is just equivalent to performing all of these row operations on the identity matrix. So that proves our theorem. Like I said, next video, I'll discuss a little bit about this, how we know that the product of these matrices was invertible as well. And then we'll do a few examples.